Welcome back, everybody. We're in section 7.5 now on inverse trig functions. So up at the top here, we've got some review, but really in the middle of this first page is the main ideas of the inverse trig function. So because sine and cosine and tangent have these periodic properties where they repeat, so for example, sine of x looks like this, we're definitely going to be failing the horizontal line test unless we restrict our domain in a very specific way. So the restriction of the domain is given in the table below, and these are ones that we derived back in 3+. We revisited them in AB, and now we're seeing them again in Calc BC, where the domain is really, really important because if we're outside of that domain, we don't actually have an inverse function, which means the only values we can use are the values of the domain that give us those specific range values. So arcsine is in the first and fourth quadrant. Arccosine is in the first and second quadrant, and then arctangent is in the first and fourth quadrant. So this table also kind of gives you range values and domain values for arcsecant, arccosecant, arccotangent. Those ones are important, but probably things that you're going to see less often than simply the arccosine, arctan, and arcsine functions. Okay, so let's go ahead and remind ourselves how to evaluate these. So arcsine of rad 2/2 is asking us if we're on the unit circle and we're the arcsine function, so we're actually only the first and fourth quadrant. What is the angle measure that's going to correspond to, in this case, a coordinate that results in a y value of rad 2/2. And so obviously that value is going to equal pi/4 radians or 45 degrees, just using our unit circle. For arccosine of 2, so we want the location on our arccosine, which is the top half there, where our coordinate is going to equal 2, and we know that that is not possible because on the unit circle your radius 1, cosine is stuck between -1 and 1, so this value does not exist. It is undefined. And finally, 3, kind of the most important example, is going to be where we have this variable expression. So sine inverse of x is saying on our sine function, where is the location where we get x for the y coordinate? So if I draw my little right triangle here, zoom in a bit. So again, we'll get x is the vertical. We know that the hypotenuse is 1, and our angle measure is here. And then our side length opposite, we can use the Pythagorean theorem to derive, is going to be 1 minus x squared, or the square root of 1 minus x squared. So what we're asked then to find is if that is our triangular relationship at that coordinate, what is the tangent of that? And so we can see, obviously, the tangent is going to equal x over the square root of 1 minus x squared from that central angle. All right. So I think we're ready to jump back in then. And there's some nice graphs here of those functions. Again, arcsine, arccotan, arccosine, arcsine, and arctangent are all important graphs to know. Arcsecants, arccotangents, arccosecant, those ones you'll see much less often. All right, so let's go ahead and derive our derivative properties for each one of our inverse trig functions. So again, what we're going to want to do is kind of draw a triangle that would be on our unit circle, but we can just draw the triangle itself if we wanted to. And so if we have arcsine of x, that means that our angle measure is going to have an opposite over hypotenuse relationship of x over 1, since that is just x over 1. And then we'll get this rad 1 minus x squared. And now we can kind of work through our expression. And note, theta equals arc sine of x here. So that's really our angle measure, is just the arc sine expression. Okay, so let's go ahead and rewrite this as sine y is equal to x using the inverse property. And then we'll differentiate both sides with respect to x. So we're going to need to take the derivative implicitly. So we'll get cosine y times y prime is equal to 1. So y prime is equal to 1 over cosine of y. But remember, y is our arc sine, so this is really, y as well. And so cosine is going to be rad 1 minus x squared over 1. So we get 1 over rad 1 minus x squared as our derivative of sine. Okay, so we'll do the same thing for cosine. So again, we're going to have a right triangle relationship. Now it's going to be x is the adjacent side, or just call it y. So we'll get rad 1 minus x squared. And again, we'll use the inverse property. So cosine of y is equal to x. So when we differentiate with respect to x, we're going to get negative sine y times y prime equals 1. So y prime is going to equal negative 1 over sine y, which when we substitute the expression for sine y, which is rad 1 minus x squared over 1, we just get negative 1 over rad 1 minus x squared. So again, that opposite relationship carries over for the inverses of sine and cosine, so they're just the opposites of each other, which is nice. And then finally, we've got tangent inverse. So if we draw our triangle, again, y is our angle measure here, and then we'll have x and 1 as our tangent relationship, opposite over adjacent, which means we're going to end up with the square root of 1 plus x squared as our hypotenuse, again using the Pythagorean theorem. So then using our inverse operation, we get tan y is equal to x. Differentiating with respect to x, we'll get secant squared y times y prime is equal to 1, which means that y prime is equal to 1 over secant squared y, but secant squared is going to be hypotenuse over adjacent, so it's just rad 1 plus x squared, but we're squaring that quantity itself. So y prime is equal to 1 over 1 plus x squared. All right, so those are our first three inverse trig properties. The next three are going to follow the same way. So let's go ahead and take a look at those. What I'll note is for tangent and cotangent, cotangent is just going to work out to negative 1 over 1 plus x squared by the same property. So it's going to have that opposite property that tangent and cotangent have as derivatives. But for secant and cosecant, we're going to get something different. So let's go ahead and look at secant, let's say. So secant, we're going to have y be our angle measure again. And then secant is hypotenuse over adjacent. So we get x and 1. So then in here, we're going to end up with the square root of x squared minus 1 as our opposite side length. Again, using the Pythagorean theorem. And then we'll do the same thing, use our inverse property. And then when we take the derivative of both sides with respect to x, we're going to get secant y tan y times y prime all equals 1. So then y prime is going to be 1 over, now it's the product, secant y tan y. And then if we look again, we can see that secant of y is just going to be x. And then tangent of y is going to be rad x squared minus 1. And so if we look at cosecant squared, it will work out the same way, where we get y prime is equal to the opposite of x rad x squared minus 1. And again, you can work that one out on your own. All right. So again, most of these you've probably memorized in some sense, but you can always, always, always derive them if you need to. And once we add the chain rule in, these are going to get messy, so just be careful with your work. And on the next page, we've got all of our derivative rules. If we apply it with the chain rule, so u is some function of x, then we need to add a u prime to each derivative. And arcsecant and arccosecant, we should note those x values, because of the domain and range, will always be positive. So we'll have absolute values on the outside here. There's not too many questions that you'll see where the domain has to be considered too closely, though, in the BC curriculum. All right, so we've got some examples below here, kind of covering all the different topics. So we'll leave that for the next video. So until next time, again, if you have questions, come by and see me during the office hours or send me an email. Otherwise,